Hello, everyone. Today in this INQA seminar series, we have with us David Haycraft from Quantum Computing Incorporated, and he recently rejoined it, and before he used to do a lot of data science. Let's hear what he has to say.
Yeah. Hello, everyone. I'm here to talk about our paper that we published on arXiv called Suppressing Unwanted Fluctuations in QAOA and Approximate Quantum Annealing. So I'm going to be going over a little bit of background on QAOA and approximate quantum annealing, which I'll refer to as AQA going forward, as well as our experimental proof of concept on IonQ, which is a NISQ device, and then going over some numerical simulation results that we also ran. And then I'll finish up with some concluding remarks. So QAOA/AQA have two components, the mixer and the phase separator. The mixer creates dynamics in the system. It flips bits to mix between computational basis states. Our implementation in this particular strategy is standard, except for that we added a zeta j to rotate some qubits more than others. That modifies the global beta, which controls the rotation. Our phase separator is identical to other implementations. The phase separator defines the problem, and it can be constructed from pairwise Pauli Z rotations. So putting these two elements together, a single stage of these algorithms involves applying the phase and mixer in sequence. So you can apply it repeatedly to obtain an implementation. So for a large L and slowly changing of gamma and beta, this can provide a good approximation of quantum annealing. Or if you're to optimize classically, that's how you would apply QAOA. So in our experimental setup, we used approximate annealing with a linear schedule. So each layer has a total rotation tau. In order to guarantee that beta and gamma are never zero, we have a parameter R, which is the current stage over the total number of stages. So L+1 over P+1. And this guarantees that they'll never be zero. So the action of the mixer applies two effects. The first is bit flipping. So it rotates the qubit and changes the proportion of 1 and 0 states. And then it also applies extra phase on coherent superpositions. The effect of extra phase is basically how is the problem encoded to obtain optimal solutions. In this case, there are some issues where the mixer is mimicking the behavior of the phase separator. And when there's a positive superpositions, it can give lower apparent energy. This is a well-known effect in quantum annealing, engineered problems, and they exhibit pathological behavior. A couple of examples are shown below here in the figures. We have on the right from Boixo and on the left from Dixon. So just to kind of ground it with a simple example here, imagine we have an 8-qubit problem as in the previous image on the bottom right. So it's been modified slightly so that there is a ground state that is the ones vector, but there are many low-lying degenerate excited states of the form 0, 0, 0, 0, x, 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 where x is either 0 or 1. And this makes it more difficult to obtain the ground state because the ground state is so far away from the low-lying degenerate excited states. So for our experiment on the gate model machines from IonQ, we implemented a simple QUBO that was 3 variables, and it has this particular behavior. One of the things to note about these types of devices is that you may not be able to build a circuit with the type of depth in which we would ideally want to for this type of experiment. So keep that in mind when we're looking at the results. So the reason why you can't necessarily build out a circuit with very large depth is because of noise. You'll see it on the right here, which is the IonQ results, that our results stray from ideal as we increase the depth, and this is due to the effects of noise. So we would expect them to align more to the image on the left if that were not the case. We can still see that there are certain effects, but it does obscure it a little bit. But next, I'm going to show you the results when we apply the suppression. And we can see that this effect is present when we locally are changing the mixer angle to reduce these phase effects. As you can see, the patterns on the left and right are still similar, even with the noise present. So in order to test our suppression strategy, we need to determine that, whether or not something can be done in actual practice. First, we need to have a method to measure the fluctuation effects. Second, we need an algorithm to convert the effects into suppression levels. 3, we need to have an appropriate set of experimental problems to test the strategy. In this case, we're building on known examples from annealing. And 4, we need to test and simulate that the results are reliable at moderate circuit depths. So right now, real quantum hardware isn't really there yet in terms of being able to run these problems at large depths. So we used a simulator. So to quantify phase effects, meaning measuring the degree of bit flipping the rest of the mixing goes into unwanted phases, we use the Fubini-Study metric, which is a formal measurement of the distance induced by rotation. For more details, see our paper. So the Fubini-Study metric is easily calculated experimentally. And the basic idea of how we used it was that for larger values, that means less unwanted phase. So we would set our zeta j based on that. And I'll show you how in just a second. So assuming we're able to measure the Fubini-Study metric for all qubits, after L-1 rotations, we can use it to set the zeta j for the Lth rotation. The suppress strategy involves setting based on the relative metric values. So using the previous stages Fubini-Study metric for a given qubit over the max across all qubits, we can set zeta j. And then for the threshold strategy, it's identical, except for it only sets it to that particular relative metric value when theta for that Fubini-Study metric is less than 0.2. Otherwise, it leaves it unmodified. So for our test problems, we selected 3 different experimental sets. So the first one was a version of the Dixon Hamiltonian with a reduced final energy difference between the ground and excited states. It was reduced by a factor of 5 to make it more difficult to find the solution. And then we also constructed random QUBOS, and as a third setting to kind of mirror a more realistic type of problem, we had an engineered QUBO which combined a max cut problem with a modified version of the more pathological example that we showed earlier. So our goal was to compare these three strategies on a fair basis for different numbers of layers. So we wanted to guarantee that as p goes to infinity, that we are approaching a faithful simulation of a quantum anneal as tau goes to 0 and p goes to infinity. And the effective runtime is p times tau. And by the adiabatic theorem of quantum mechanics, we are guaranteed that this protocol will give us 100% success. For our particular experiments, the total rotation per stage was tau is equal to pi over 2 times p to the 1/4. So for the Dixon-Hamiltonian, we can see the results for the success probability in this graph here. So the suppressed strategy is in orange and the threshold strategy is green, and then the blue will be the unmodified version of the algorithm. So for this particular problem, suppression/thresholding did not offer improvement because at low depths, the best success probabilities are yielded for this particular problem. However, as we see in the mid-teens, the suppressed and the thresholded version do outperform the unmodified version of this particular problem. So some supporting evidence for there being a mechanism here for why this particular strategy would work. We can look at the Fubini-Study metric to see that as P gets larger, that metric gets much lower and continues to decrease. Whereas with the suppressed and threshold strategy, it hovers at 0.2. This lends evidence that the strategy is in fact working at higher depths. So for our next test set of problems, we had random QUBOS. The suppressed and thresholded strategies both performed identically, and this is because, or I'm sorry, the suppressed and unmodified versions both performed identically because the thresholds were never reached. So basically, this type of problem didn't exhibit that type of pathological behavior that I explained earlier. And the suppressed strategy did perform significantly worse. We're not really sure why that's the case. That might be an area for some future exploration. But I think it is a good thing to note here that the threshold strategy also did not kick in and make the overall quality of the solutions worse. Finally, for our engineered problem here, we have the Dixon-Hamiltonian combined with the max cut problem to provide a more realistic hard optimization problem. Since our other two examples either didn't have the pathological feature or aren't extremely difficult in terms of their actual optimization. So we wanted to find a problem that kind of combined both those attributes. So this last example shows that the thresholded and suppressed strategy both outperform the unmodified version, as well as optimized QAOA schedule. So we can see that the thresholded strategy continues to improve at a much greater rate than both of the others, although the suppressed strategy does begin to outperform the unmodified strategy, again, in that mid to low teens area in terms of the depth. So why is this the case? Why does QAOA underperform in this particular case? So QAOA doesn't have as much control since there is no zeta j. So you don't have as many parameters that you're optimizing over. Also, the average energy as an objective would be prey to the false minimum at those low energy states, where we have many identical solutions that have similar energies that would be considered to be good by that particular type of objective. So long story short, traditional QAOA approach doesn't really help with this particular problem. And in an attempt to generalize the behavior, we tried 25 randomly generated instances of the engineered problem of size 10 qubits. And this is a plot of the cumulative distribution. So basically, we arrange each of the instances from lowest to highest success probability. This graph is displaying for p equals 50. We can see that the threshold inversion outperformed at every single point here. So on average, the threshold inversion's performance was roughly, or I should say the median performance was roughly 40% success probability. And then the median performance for the threshold inversion was roughly 25%. And then the median performance for the unmodified version was around 15%. So just some concluding statements here. So I think these experiments show that these effects are visible at moderate depths on current hardware. So for these types of problems, you will run into them no matter if you're using a quantum hardware or a simulator. We can counteract these phase effects that are known to be problematic in annealing and have been identified in multiple different circumstances. And this strategy, it uses degrees of freedom, which are not typically exploited in QAOA, so it could be used in tandem with other strategies. And finally, this was just a simple proof of concept. We used a single metric. We didn't really compare it to any other way of doing this particular suppression strategy. There may be better strategies for handling the thresholding, as well as potentially a different metric that may perform better. And finally, we don't really know why the suppression strategy underperforms the unmodified version on the random QUBO case and other problems. It's not clear, so that would be an interesting area to potentially be a jumping off point for this for future work. Finally, I appreciate you all taking the time to listen to me, and I just wanted to acknowledge my co-authors, Quantum Computing Inc. and IonQ for the free machine time and the useful discussions we had with Daiwei Zhou. Here's our contact information, and yeah, I'll open it up for questions now.
Yeah, thanks for a great talk. Is there any questions? Good, so I can ask one question. It seems that to implement your strategy, you need to do a lot of intermediate runs with measurements of X operators. So can you give some details on to how many actual runs do you need to kind of find this particular combination of drivers that you use?
I can't remember the exact details. Can I pass that over to you, Nick?
Sure, yeah, of course. So with this, what we consider, so for each one of these, we need the value of the X at L-1 depth or number of stages. So for what we've done here, you would need to do several, or basically up to the total depth, you'd need to do one at each shorter depth. So for instance, if we had p equals 20, we'd need to do one at L equals one at, which just does the first one, then the first two, then the first, et cetera, all the way up to 19, in addition to the final run. So these are hard optimization problems, and this is sort of a polynomial overhead, so maybe it shouldn't be so worrying. one thing you could consider to get around this is potentially to use a strategy that's only thresholding and just pick a value that you reduce these by. And then that would just require one run, not one for each P up to our value. But yes, that is a good observation that that this does require you to do some extra runs to implement. You don't get this information for free.
Right. Yeah. Thanks. So usually I would compare the two strategies for the same total number of runs, but I guess this kind of comparison is probably more. I guess it allows you to more clearly see what's the underlying physical effect. Right. Any
Yeah.
other questions? Good. So with that, I will stop the recording.